All right, in day one, part two, we're going to take a look at a very important data structure called a binary search tree. It's a relatively simple kind of tree in which you can store some arbitrary number of values in a sorted order. In our case, we're going to store the values in ascending order from the leftmost branch to the rightmost branch. Basically, a binary search tree consists of a collection of nodes hooked together by references, and we need to be able to compare values in whatever data type we're storing in the tree for order, that is, for less than and greater than ordering. For simplicity of interacting with the binary tree, it's very important to understand recursion. A binary tree is an inherently recursive kind of data structure. So this will give us a chance not only to talk about a very important data structure, but also to get a lot of practice using recursion. The binary search tree is a very important data structure to know very well because it's the simplest case of many other kinds of trees that you're likely to encounter. Okay, so here on slide 3, we're just showing a diagram of a potential binary search tree with 6 items added to it. The box in the upper left corner represents the binary search tree object, and within that binary search tree object we have an attribute called top that refers to the topmost node in our binary search tree. That node will contain the first value that was inserted into the binary search tree. So in this case, in this example, apparently 12 was the first value that was inserted into this binary search tree. Now each node in the tree has a data value and a left and right child. So the left child refers to the topmost node in a tree of values that are all less than 12, and the right child refers to the topmost node in a binary search tree of values that are all greater than 12. So this entire thing is a binary search tree, but recursively the left-hand side is a binary search tree and the right-hand side is a binary search tree as well. Okay, so let's turn this diagram into some code. I have uploaded to Canvas this file, binarytree.py, and we're going to go through the code in this binarytree.py implementation of just a few of the methods that a binary search tree should support. Binary tree is going to be a class, so we can create and interact with binary tree objects. All right, so this box in the upper left corner of our diagram represents the binary tree. And for now, in this implementation of our binary tree, the only instance variable that we're going to need is top, actually underscore top, to indicate that this is private. This should be respected as private within a binary tree object. And initially, notice this is the init function, initially the top is going to refer to no other nodes. So when we create a brand new binary search tree, that is a brand new binary tree, the tree is going to be empty and underscore top is going to refer to the value none. Now, within the binary tree class, we have a nested class underscore BT node. And this nested class is going to allow us to create objects that have these 3 instance variables that define what each node in the tree looks like. So there's going to be a value, which we're going to store in the underscore value instance variable. And then there's going to be a left tree and a right tree, that is references to the left-hand side and the right-hand side. Notice that in our init function for the BT node class, the default value for these left and right are none. So when we create a brand new BT node, we will store some value that was passed in, but left and right by default are going to be none. We have the opportunity to pass in different left and right values, But in the implementation that we're going to look at here, left and right are always going to be none. Okay, so let's take a look now at the top of an application making use of this binary tree class. Here on the left-hand screen, we have our application file, bt_app.py. Of course, the first thing the application needs to do is to import the binary tree module so that it can make use of the binary tree class and interact with binary tree objects using methods. We're going to import the binary tree module as BT. Then, in order to create an initially empty binary tree object, we'll simply say bt.binaryTree, and that will invoke the init method over here from the binary tree class to establish an empty binary tree. All right, so what that's going to do is to initialize the _top instance variable within the binary tree object to none. And diagrammatically, we're going to end up with a binary tree object being created and with its _top instance variable referring to none. A reference to that newly created binary tree object is going to be returned from this binary tree constructor, and we're going to store that reference into this variable bt1. Okay, so now we have a binary tree object. We're referring to that binary tree object using the variable bt1, and at this moment, the binary tree is empty. It exists, but it's empty. It exists, but it has no nodes. Okay, so now that we have our empty binary tree object, we want to be able to insert values into this binary tree object. In the insert method here for the binary tree, self is a reference to the binary tree object. Value is going to be the value that we want to insert into the binary tree. Now, there are two possible cases that insert has to worry about. One case is where the tree is empty. That is the case where self._top is none. If the tree is empty, then we simply want to create a binary tree node containing our value, and we want to modify the binary tree's _top instance variable to refer to that newly allocated BT node object. But on the other hand, the tree might already have stuff in it, in which case, if _top is not none, we're going to want to use a recursive function that will figure out where in the already existing tree of nodes to insert this new value. We're going to call our recursive function InsertHelp. The existing node under which we're going to want to insert this new node is _top when we're at the top level of the tree, and value is the value that we want to insert into the tree. So let's take a look first at the case of an empty tree. That's the case that we started out with here on slide 5. On slide 7, we've added an insert into our binary tree. Here, self._top was equal to none, so we're going to modify self._top to refer to a newly allocated BT node. Let's remind ourselves what this BT node class is about. All right, here's the BT node class. I'm passing in the 12, and I'm not passing any values for left and right, so those are going to be none by default. Consequently, the init function in the BT node class, _BT node, is going to create an object, initialize the value part to 12, initialize left to refer to none, and initialize right to refer to none. All right, so there is our newly allocated BT node. And rather than cluttering up the screen, by having the underscore left side refer to none and the underscore right side refer to none. It's common in a diagram to just have empty boxes for the left and right references to indicate that they don't currently refer to any node. We're modifying underscore top to refer to that newly allocated node, and we're done. Okay, so we've inserted the topmost value into the tree. Now our tree has one value in it rather than no values as it originally did. Let's trace through next what happens if we do already have a value in the tree, and we're going to insert another value. So here on slide 8, following our insert of 12, that was the first value, we're going to do another insert, this time of 7. All right, so self is the binary tree object, value is 7, self._top is not none at this point because we do already have one value in the tree. Consequently, we come down to the else and we say into the binary tree, let's do an insert help of self.top. Okay, that refers to the node containing the 12. And our value is 7. All right, so here we are now in our insert help method. Insert help is receiving 3 parameters. The first parameter is a reference to the binary tree object itself. The second parameter is a reference to the top node. All right, so the second parameter is a reference to this node. And the third parameter is 7, the value that we want to insert. Now, our rule for the way that this binary search tree is structured is that if the new value we're adding is less than the current node's value, we're going to insert that new value to the left side. Otherwise, if the new value was greater, we would add it to the right side. But in this case, 7 is less than 12. Okay, 7 is our value. Curnode._value is 12. That's the value in the current node. And because 7 is less than 12, and because the left side of curnode, okay, here's curnode, curnode._left is none. Consequently, we're going to modify curnode._left to contain a new binary tree node with that value 7. Okay, so actually what's going on here, we're testing whether curnode._left is none. That's very similar, except one step further down in the tree from testing whether self._top was none. If the tree itself was entirely empty, we added a node at the top of the tree. Now we've discovered the bottom of the tree on the left-hand side, and we're adding a new node to that left-hand side. All right, so we've now inserted 12. That was our topmost node in the entire tree, and 7 is the node to the left side of the 12. Okay, so on slide 6, we showed the insert method that handles the two cases of an empty tree and a tree that contains at least one node already. We only had room to look at the very topmost part of the insert help code, where we were inserting a lower value than the existing node to the left, assuming that the left was the bottom of the tree. On slide 9, we're going to show the remainder of the insert help code. All right, and so now here we're able to handle both situations where the value that's being passed in is less than the current node, or the value that's being passed in is greater than the current node. Within each of those possibilities, where the value is less or the value is greater, we're handling both the case of having reached the bottom of the left-hand side or having reached the bottom of the right-hand side, or having to continue recursively calling insert help either on the left or on the right in order to discover where the bottom of the tree is so that we're able to figure out where to put our new value. Okay, so here on slide 10, continuing with our application code, we started out by creating an empty tree. We then inserted 12, which became the topmost node in the tree. We then inserted 7 to the left of the 12. When we did that, the 12 was the bottommost node in the tree. So we were able to add the BT node containing 7 as the left child of the 12. Well, now our tree has 12 and 7 in it. We're going to insert 13, and then we're going to insert -4. Let's walk through quickly what's happening here. So we called insert. Insert discovered that there already was a node at the top, and so insert calls insert help to figure out what to do next. In insert help, self refers to the binary tree as a whole. Cur node is a reference to the BT node containing the 12, and value is 13. In this situation, 13 is not less than 12, so we drop down to elif and we ask whether 13 is greater than 12. Since 13 is greater than 12, and since the right side of the 12 is none, we allocate our new BT node on the right side of the 12 and fill that in with a 13. So that's what causes this node containing 13 to be added to the right side of the 12. And at that point, we're done. Now, continuing on to the insert of -4, let me erase some of my yellow here. All right, so now we're inserting the -4. When insert gets called, we discover that the binary tree BT1 has a node in it. So we call insert help. Self is a reference to the binary tree as a whole. Cur node is a reference to the 12, the topmost node in the tree. Value this time is -4. Okay, so we discover that -4 is less than 12. However, curnode.left is not none. Curnode.left is the node containing the 7. So we drop down to else here and we call insert help, passing the node containing the 7 and -4. So here we have a recursive call of insert help. Self still refers to the binary tree as a whole. Cur node is a reference to the node containing the 7. Value is -4. -4 is less than 7. And 7 is at the bottom of the tree. So curnode._left, the _left instance variable in the node containing 7 is none. And consequently, I modify the _left instance variable in the node containing 7 to refer to this newly allocated binary tree node containing -4. And so that adds the green node, the -4, down to the left of the 7. And we can continue on inserting more values. And each value we will recursively descend through the tree, either to the left or the right, depending on the relative values, until we find the bottom of the tree. And at that point, we will allocate our new node and modify our reference to refer to that newly allocated node. I did want to point out one thing here, which is that I'm testing both less than and greater than. The implication here is that it's not going to be possible in this binary search tree to have duplicate values. My tree already has a value of 12 in it, so let's suppose I insert 12 again. In the insert function, I'll discover that the tree already contains a node. So insert help is going to be called with self referring to the binary tree as a whole, cur node referring to the node containing 12, and the value that I'm trying to insert is also 12. Well, 12 is not less than 12, so I drop down to elif. 12 is also not greater than 12, so that's it. Nothing happens. The 12 does not get inserted a second time. Okay, so now we know how to create binary tree objects using the binary tree classes init function. We also have a way of inserting values into the binary tree in order using the insert method and its recursive insert help function. Next, we want to take a look at how we can represent the contents of a binary tree as a string so that we can display what is currently within the binary tree. All right, so in order to convert a binary tree contents into a string, we will need to define our __stir__ method, shown here on slide 11. Self is a reference to the binary tree object as a whole. The values stored within the binary tree are stored recursively in these BT node objects. So what we'll do in our __stir function is to call this recursive help function that will return to us a string representation of the values within the binary tree. Okay, so we're passing in self._top to the stir help function. Now here on slide 12, I have created a new binary tree object, BT2. This is an empty binary tree. Of course, our __stir__ method has to be able to properly handle representing an empty binary tree. So let's see how we're doing that. In our _stir help method, self refers to the binary tree as a whole. Cur node is the current node that we're referring to. In this case, the current node that we're referring to is the _top instance variable's value, and that is none in the case of an empty tree. So we're going to do an extremely trivial thing in the case of an empty tree and just return an empty string to represent an empty tree. Now, in this print function call here, print is going to display two things. First of all, it's just going to display this string, bt2:, followed by a space. So the output is bt2:, followed by a space. In order to print the bt2 object, print will automatically invoke the stir function on bt2. That will invoke the __stir__ method on the object bt2, which is simply going to end up returning an empty string. So when I call this print function, all I get out is bt2:, space, and then an empty string. So bt2 is empty. Here on slide 13 is the remainder of the _stir help recursive function, in which we have the part of code that we need for handling a non-empty tree. On slide 14, we're reminding ourselves what BT1 currently contains. BT1 is a binary tree object where _top refers to a hierarchy of 4 BT nodes. And let's walk through what happens when BT1 is printed. Okay, so when BT1 is printed, the stir function is automatically called. The __stir__, That's difficult to say very often. That function calls stir help, passing in a reference to the topmost node, that is a reference to the node containing the 12. This time, the node containing 12 is not empty. So, what am I going to do? Well, I want the 12 to be displayed in the correct location relative to the other values in the tree. What that means is that I want to generate a string representing the left-hand nodes in the tree, the -4 and the 7. I also want to generate a string containing the right-hand nodes in the tree, the 13 in this case. And in between those, I'm going to display a string representation of the current value, which is 12. Okay, so the left string might be empty, but assuming that the left string is not empty, what I need to do is to take the left-hand side and append a space followed by the current value, the 12. If the right-hand side is not empty, I'm going to modify my return value to be that current string appended with a space and the right-hand side. Okay, and because stir help is being called recursively here, what I'm going to end up getting out as the eventual return value from the top level call of stir help is -4 space 7, that's the left-hand side, and then a space and the current value, which is 12, and then another space and the right-hand side, which is 13. All right, so my output is -4 space 7 space 12 space 13. We can argue about whether this is an appropriate way to represent a binary tree as a string, but certainly this is a compact way that does show the values that the binary tree contains in ascending order. Okay, so now we're really getting somewhere. We can create binary trees. We can insert values into binary trees in ascending order in our case, and we can also display a representation, a trivial representation of the contents of a binary tree because of the way we've defined our stir function, that is the __stir___ method. Now we want to think about other methods that it would be convenient to have for interacting with and finding out about our binary tree. One such method is the sum method, shown here on slide 15, that simply computes and returns the sum of all of the values stored in the binary tree. Here again, because the structure of the binary tree nodes is inherently recursive, I'm going to call an _sum help function to actually do the computation. And this is fairly easy. If the current node, that is the topmost node, when we first enter the sum help function is none, we'll just arbitrarily say that the sum of that value is 0. So 0 is going to be our default value for an empty tree. Otherwise, if the tree is not empty, then the sum of all the values in the tree is simply the sum of all the values from the left-hand side plus the current node's value plus the sum of all the values from the right-hand side. And you'll notice that I have put a pair of parentheses around this to make sure that I can type this on multiple lines. All right, that's it. So that's very simple. Here is an example on slide 16. We're looking at BT1, which still contains 12 with left and right children of 7 and 13, and 7 in turn has a left child of -4. The sum is therefore going to be the sum of the left plus 12 plus the sum of the right. Well, the sum of the left is the sum of the left plus 7 plus the sum of the right. The sum of the left here is just -4. The sum of its left is 0. The sum of its right is 0. So -4 is the sum of the left. -4 plus 7 plus 0 is 3. And 3 plus 12 plus the sum of the right, which is 13, gives me 28 as my sum. And of course, that's just one of many methods that we can create for interacting with or finding out about or even rearranging the nodes in our tree. Well, let me say a word about performance here. Ideally, if the values are inserted into the tree in some kind of random order, then the tree will be fairly bushy, and you'll have both an insert and search time of order log n. That is, it will take you log n time to figure out where to put a new value, and it will also take you log n time to determine whether a particular value is in the tree or not. However, a serious problem with the binary search tree we've shown here is that if values come in a sorted order, and this doesn't matter whether it's ascending order or descending order, your binary so-called tree is actually going to be shaped like a list. Either all the values will march down the right side of the tree if the values are coming in ascending order, or the values will all march down the left side of the tree if they're coming in descending order. And consequently, in that kind of situation, both inserting and searching are order n operations rather than order log n operations. There's a whole family of so-called self-balancing binary search trees that enforce order log n performance in all cases, regardless of which order the values are inserted into the tree into. And we'll talk about these early in the spring in Financial Computing 2. All right, so that's that, and in your homework you'll have an opportunity to add a bunch of additional methods to the implementation of this binary tree.